In this video, we're going to talk about some more examples of computing limits using the limit laws that we discussed previously. So first, we're going to do an example where we have a graph. So here we have the graph of two functions, f of x and g of x. And we want to compute the following limits. So we want to compute the limit as x goes towards negative 2 of f of x plus 5 times g of x. And so remember, for our limit properties to work, we have to check that the limits actually exist. Now at minus 2, we see that the limit of g of x is going to be approaching negative 1. So as we approach negative 2, we're going towards this point, which is negative 1. And the limit as x approaches negative 2 of f of x is going to be equal to, here we're approaching this point of 1. Even though it's defined differently at negative 2, it's defined to be 2, we're approaching that open circle, which has a value of 1. And so here we have the value of both of those limits. So now we can use our limit properties to say that the limit as x goes to negative 2 of f of x plus 5 g of x equals the limit as x goes to minus 2 of f of x plus the limit as x goes to minus 2 of 5 times g of x, which is the limit as x goes to minus 2 of f of x plus 5 times the limit as x goes to minus 2 of g of x. Now plugging these in, f of x goes towards 1, and g of x goes towards minus 1, so we get 1 plus 5 times minus 1, which is 1 minus 5. So we get negative 4 for this limit. Now the key thing to be aware of here is we did need to check that the limits existed before we could actually use limit laws. Now frequently we just kind of assume the limits exist and use the limit laws, but we should actually check that limits exist before applying our limit laws. And so another example that we can look at for this same graph is the limit as x goes towards 1 of f of x times g of x. And so here, once again, we need to check that the limits exist. So as we go towards 1 for f of x, looking in the graph, we can see as we go towards 1 for f of x, which is the red graph, we're going towards this point here, which that point there is the point 1, 2. And so we're approaching a value of 2. And then the limit as x goes to 1 of g of x. Looking on our graph, we see that if we approach from the left, g of x, we get negative 2. But if we approach from the right, we get negative 1. So in this limit, we get different things for the left hand and the right hand side. And so it's actually the fact here that the limit in this case does not exist. And now because these limits do not exist, this suggests that this overall limit won't exist. But what we're going to do is we're going to consider right hand and left hand limits for g of x, just to make sure. So if we approach from the right one of g of x, in the graph we saw that went towards negative 1. And if we take the limit as x goes towards 1 from the left of g of x, we get minus 2. And so now using our limit properties, we have the limit as x goes to 1 from the right of f of x times g of x. So the limit as x goes to 1 of f of x times the limit as x goes to 1, both from the right of g of x, which f of x goes to 2, and g of x goes to minus 1, so we get negative 2 here. Then if we take the limit as x goes towards 1 from the left of f of x times g of x, we get the limit as x goes to 1 from the left of f of x times the limit as x goes to 1 from the left of g of x, which is 2 times minus 2. So we get minus 4. And now notice that the limit from the right and from the left are not the same. And so this limit does not exist. Now the key thing to note here is we did still need to check the one-sided limits even though we knew the limit of g of x did not exist. Because it is possible that the two-sided limit actually still existed. That perhaps the values of g of x, even though they didn't exist, when you multiplied by f, you got the same value from the left and the right. Now that's only likely to have happened had the limit of f of x been 0. So this limit been 0 rather than 2. Then we would have gotten 0 for both of them, and the product would have existed. And so that was a possibility, so we did need to check both the one-sided limits to make sure, even though we knew g of x's limit did not exist. But that's kind of a rare case where that would happen. So next, let's compute the following. We have the limit as x goes to negative 1 of x plus 1 over x cubed plus 1. And so notice if I tried to plug negative 1 into the bottom here, I'd have negative 1 cubed plus 1, which would give me 0. So because of that, we can't just plug negative 1 directly in. So we're going to try to factor the denominator. And so we have the limit as x goes to 1, not 1, negative 1. So it's negative 1 of x plus 1, and then factoring the bottom, x cubed plus 1 factors as x plus 1 times x squared minus x plus 1. Now, just as a side note, you can check that by actually multiplying this out. So you'd get x cubed plus minus x squared plus x, and then distributing the x to every term, and then distributing the 1, you'd get minus x squared, plus x squared, minus x plus 1. And then notice the plus x and the minus x cancel, the x minus x squared and plus x squared cancel, and so you're just left with x cubed plus 1. And so that's just verifying that that product actually is true, that it does factor as I claimed. So this then would be the limit as x goes to minus 1. Now notice here we have an x plus 1 on the top and on the bottom, so those cancel because we're approaching when that would be 0, but we're not actually at that place. So this then gives us 1 over x squared minus x plus 1. And now you can check that if we plug in negative 1, we don't have any issues now of dividing by 0, so we'll have 1 over negative 1 squared minus negative 1 plus 1, which is 1 over 1 plus 1 plus 1, which is 1/3. And so we see in this limit, we got a value of 1/3 using our limit properties. Next, let's take the limit as x goes towards 2 of 2 minus x divided by the square root of x plus 2 minus 2. So now, as a reminder, when we have a radical appearing in the expression, and we can't just plug things directly in, which you can check if you plug in 2 on the bottom, we're going to have the square root of 4 minus 2, which is 2 minus 2, which is 0. So we can't just plug in 2. So what we do is we multiply by the conjugate to rationalize where the square root appears. And remember, the conjugate just means I change one of the signs in the expression with the square root. So this is going to be the square root of x plus 2 divided by the square root of x plus 2 plus 2. And so I'm doing this because it's doing the difference of squares formula in the bottom to cancel things out. And so we'll get the limit. So x goes to 2 of 2 minus x times the square root of x plus 2 on the top. Then on the bottom, just to reiterate, we're going to have the square root of x plus 2 all squared plus 2 square roots of x plus 2 minus 2 square roots of x plus 2 minus 4. And so that just comes from distributing out that product in the denominator. Now if we simplify this, we'd have the limit So x goes to 2 of 2 minus x times the square root of x plus 2 on the top, then divided by x plus 2 minus 4. And so simplifying the bottom, we have the limit. So x goes to 2 of 2 minus x times the square root of x plus 2 divided by x minus 2. Now you might be tempted to multiply out the top. However, when we're doing this multiplying by a conjugate, it's usually easier not to actually multiply out the piece that doesn't have the conjugate in it. Meaning that the top is not what I multiplied by the conjugate of, it was the denominator I multiplied by the conjugate of, so it's usually easier not to actually multiply out the top. Usually the cancellation will be something that has to do with the term that we had factored out already. And so here, now we're going to factor a negative out of the top to make x minus 2 show up on the top. So if I factor a negative out of the first term, I have negative x minus 2. So notice if I multiplied negative 1 through, I'd get the 2 minus x we had before. Then times the square root of x plus 2 divided by x minus 2. So now I have an x minus 2 on both the top and the bottom, so I can cancel those out to be left with the limit as x goes to 2 of negative square root of x plus 2 plus 2. And so now we want to compute this limit. And so just to be clear, the negative is multiplying this whole thing. So I can pull the negative out to get negative limit as x goes to 2 of the square root of x plus 2 plus 2. Then using limit properties, this is negative limit as x goes to 2 of the square root of x plus 2 plus the limit as x goes to 2 of 2, which equals the negative of the square root of the limit as x goes to 2 of x plus 2 plus the limit as x goes to 2 of 2. Now I can just plug things in, so I have negative the square root of 2 plus 2 plus 2. So I have negative square root of 4 plus 2. Now the square root of 4 is 2, so I get negative 2 plus 2, which is negative 4. So we get this whole limit that we were computing was equal to, this limit right here, was equal to negative 4 in this computation. So next, we're going to look at a bit more complicated of a limit. We will see these kinds of limits later on as well. So we're going to have the limit as h goes to 0 now instead of x of 1 over x plus h squared minus 1 over x squared, all divided by h. So now we didn't talk about what to do in this kind of limit in the last video, but what we do here is we're going to combine the terms on the top by getting a common denominator. So this is sometimes called cross-multiplying. I'm going to multiply the first term on the top and the bottom by x squared, and the second term on the top and the bottom by x plus h all squared. So the first term is going to be x squared over x squared times x plus h squared minus x plus h all squared times x squared divided by x squared times x plus h all squared. This is all over h. So now I'm doing this, so now I have a common denominator in the numerator of this expression, so I can combine things to get the limit as h goes to 0 of x squared minus x plus h all squared divided by x squared times x plus h squared divided by h. So now we're going to do a trick to kind of fix the problem that we have a mixture of fractions here. And so remember that when we have a division, it's the same as multiplying by the reciprocal. So this is equal to the limit as h goes to 0 of x squared minus x plus h all squared divided by x squared times x plus h all squared. Then I was dividing that by h, which would be the same as if I multiplied by its reciprocal, which is 1 over h. And so this whole expression then is the limit as h goes to 0 of x squared minus x plus h all squared divided by x squared h times x plus h all squared. And so this is a trick that just let us write it as a single fraction rational expression rather than the complex multiple fraction that we had. So now we're going to multiply out the top. So we have the limit as h goes to 0 of x squared minus, multiplying out x plus h all squared, we get x squared plus 2xh plus h squared, all divided by x squared h times x plus h all squared. And kind of like in the last expression, the last problem, it's usually easier not to multiply things out when you're doing limits. It's usually easier to leave things as just products of things unless you have a subtraction like we did here. So we were doing x squared minus the product of something rather than just a product of multiple things. So it's easier to multiply things out in that case. Well, in the bottom, it's just a product of 3 things. And in that case, it's usually easier not to multiply it out. And so now we're going to distribute the negative that we have on that one term in the numerator. So we have x squared minus 2xh minus h squared, all divided by x squared h times x plus h all squared. So now notice we have a plus x squared and a minus x squared on the top. So this simplifies to be the limit as h goes to 0 of negative 2xh minus h squared, all divided by x squared h times x plus h squared. So now notice that we have an h multiplying everything in the numerator, and so I'm going to factor that off. So factoring that off, I have the limit as h goes to 0 of h times minus 2x minus h divided by x squared h times x plus h all squared. Now I have an h in both the top and the bottom multiplying everything, so this h can cancel with this h. And I'm left with the limit as h goes to 0 of negative 2x minus h divided by x squared times x plus h all squared. And now if I tried to plug h in, this is just a rational expression, so I can just plug things in. If I try to plug h in, I'm not going to get 0 in the bottom. And so I can do so using direct substitution that we talked about last time. So this is negative 2x minus h, but h is now 0, divided by x squared times x plus 0 all squared. And so this becomes negative 2x divided by x squared times x squared, which is negative 2x over x to the 4th. And that then becomes negative 2 over x cubed. And so now this problem is a little bit different, as x was not the thing we were taking the limit of. We were taking the limit as h goes to 0. X was just some variable showing up, or some letter showing up. And so we don't actually do anything with it. We'd expect x's in our final answer, since we weren't taking the limit as we were approaching x going to anything. So now the last example we're going to look at in this video is the limit as x goes to minus 2 of 2 minus the absolute value of x divided by 2 plus x. So remember that when we see a piecewise function, which absolute values functions are piecewise, remember it's absolute value of x is x if x is greater than or equal to 0, and negative x if x is less than 0. We always want to do this in 2 pieces. And so we're going to do it in 2 pieces. So we'll take the limit as x goes towards negative 2 from the right of 2 minus the absolute value of x over 2 plus x. And so now when we plug in values really close to negative 2 but above negative 2, we're still going to be plugging in negative. So we'd be plugging in things like negative 1.9 which is still negative, so the absolute value of x becomes negative x in this limit. And so then we'd have the limit as x goes to negative 2 from the right of 2 plus x over 2 plus x, which is the limit as x goes to negative 2 from the right of just 1, which equals 1. And so we get 1 for the right-hand limit. And so now we're going to take the left-hand limit as well. So we take the limit as x goes to negative 2 from the left of 2 minus the absolute value of x over 2 plus x. So we have the limit as x goes to negative 2 from the left of 2 minus. Now, when we plug in values to the left of negative 2, we're going to plug in things like negative 2.01, so they're still negative, so the absolute value of x still is negative x, and we're still dividing by 2 plus x. So we have the limit as x goes towards negative 2 from the left of 2 plus x over 2 plus x. And by the same argument as above, this will just be 1. And so what we found is in this whole limit, we got a value of 1. And now the reason why these two limits ended up being the exact same computation is the fact that the absolute value of x only changes what it's equal to when you're near 0. But we weren't approaching 0. We were approaching negative 2. And so the absolute value of x was the same function in both cases because we weren't approaching where it changes formulas. And that's true in general for piecewise functions. So if you have a piecewise function that you're taking a limit of, and you're not approaching where it changes formulas, you don't really need to split it up into two pieces like we did here. But if you are approaching where it changes bounds, so in this case, if we had been approaching 0, then we would have needed to actually split it up like we did. But since we were approaching negative 2, it was not necessary to split it up.